Welcome to our channel. Today, we dive into an incredible journey of innovation, resilience, and scientific breakthrough. This is the story of how a low-cost neutron imaging system was developed against all odds. It all started when Mr. Sklenka reached out to Mr. Schillinger, seeking advice on replicating a low-cost neutron imaging system pioneered by the FRM research reactor team.
Of course, I'd be happy to help. Let's discuss the design and parts needed.
Mr. Schillinger then connected with Miss Matushkova via video calls, providing detailed guidance on the system's design and sourcing necessary components.
With this information, I think I can build the system at home.
With patience and determination, Miss Matushkova successfully built the neutron imaging system in her home. She first tested it using visible light to ensure everything was in working order. Once COVID-19 restrictions were lifted, Miss Matushkova installed her system at the Czech Technical University reactor. She successfully produced the first two-dimensional digital neutron image at CTU. The breakthrough didn't stop there. By exposing the system to neutrons for 12 hours at 500 watts, Miss Matushkova produced a neutron tomographic image. This process was much faster and required significantly less power than traditional research reactors. Now pursuing her PhD, Miss Matushkova is refining the neutron imaging system, which is used for both education and research. One notable project involves examining cultural heritage artifacts with the National Gallery in Prague. The success of the low-cost system at CTU demonstrated that such systems could be used globally. Mr. Schillinger and Mr. Aaron Kraft from Idaho National Laboratory led a mission to install a digital neutron imaging system at the 1Rech research reactor in Chile.
We're here to help research reactors worldwide benefit from this technology. It's a game changer for education and scientific research.
The IAEA supports this initiative by dispatching expert missions, procuring equipment, and offering comprehensive training. They've also published guides on neutron imaging and expanded e-learning opportunities. In 2022, the IAEA facilitated Ms. Matushkova's 4-month stint at the RA6 reactor in Argentina, where she helped set up a low-cost neutron imaging system. Similar systems are now operational at the IAEA's Neutron Science Facility in Siebersdorf, Austria, combining X-ray and neutron imaging for advanced training. But what exactly is neutron imaging? It's a non-invasive method to examine the internal structures of opaque objects, similar to X-ray imaging. However, unlike X-rays, neutrons penetrate most metals and rocks, but are attenuated by lighter elements, revealing unique insights. Thanks to the dedication of scientists like Ms. Matushkova and the support of international collaborations, neutron imaging is now more accessible than ever. This revolutionary technology opens up new possibilities for research, education, and cultural preservation worldwide.
Imagine seeing through solid objects, not with X-ray vision, but with something even more powerful. This is the promise of neutron imaging, a technology that uses the subatomic particles of the atom's nucleus, neutrons, to reveal the inner secrets of objects. Neutron imaging is not new. It has been around for decades. But recent advances in neutron sources and detectors have made it more powerful and versatile than ever before. This has opened up a whole new world of possibilities, from inspecting aircraft engines for defects to studying the flow of fluids through porous rocks. Neutron imaging works because neutrons interact with matter differently than light or X-rays. Neutrons are electrically neutral, so they can penetrate deep into materials without being deflected or absorbed. They also interact strongly with the nuclei of atoms, which means they can provide information about the composition and structure of materials. This makes neutron imaging an ideal tool for studying a wide range of objects, from biological samples to cultural artifacts. It is also being used to develop new materials and technologies, such as more efficient batteries and lighter, stronger aircraft components. X-rays are a familiar tool for seeing inside objects. They are used in hospitals to diagnose broken bones and in airports to screen luggage for contraband. But X-rays have limitations. They are not very good at distinguishing between different types of materials, and they can damage delicate objects. Neutron imaging overcomes these limitations. Neutrons can easily distinguish between light elements like hydrogen and carbon, which are difficult to see with X-rays. This makes neutron imaging ideal for studying biological materials, such as cells and tissues. Neutrons are also less damaging to materials than X-rays. This makes neutron imaging a valuable tool for studying delicate objects, such as cultural artifacts and fossils. In fact, neutron imaging has been used to study the Dead Sea Scrolls, revealing hidden text that was invisible to the naked eye. Neutron imaging is being used in a wide range of industries, including aerospace, automotive, energy, and manufacturing. In the aerospace industry, neutron imaging is used to inspect aircraft engines for defects. Neutrons can penetrate through the metal casing of an engine and reveal cracks or other defects that could lead to engine failure. In the automotive industry, neutron imaging is used to study the flow of fuel and oil through engines. This information can be used to improve engine efficiency and reduce emissions. Neutron imaging is also being used to study the structure of batteries, which is important for developing more efficient and longer-lasting batteries for electric vehicles. In the energy industry, neutron imaging is used to study the flow of fluids through porous rocks. This information is used to improve the efficiency of oil and gas extraction. Neutron imaging is also being used to study the structure of nuclear reactors, which is important for ensuring the safety and efficiency of nuclear power plants. In the manufacturing industry, neutron imaging is used to inspect welds, castings, and other components for defects. Neutrons can penetrate through metal and reveal defects that could lead to product failure. Neutron imaging is also being used to study the structure of materials, which is important for developing new materials with improved properties. Neutron imaging is a rapidly developing technology with enormous potential for the future. One of the most exciting areas of development is the use of neutron imaging in medicine. Researchers are exploring the use of neutron imaging to diagnose and treat cancer. Neutrons can be used to target cancer cells without harming healthy tissue. Another promising area of development is the use of neutron imaging in security. Neutron imaging can be used to detect explosives and other hazardous materials. This technology could be used to screen luggage at airports and other sensitive locations. The development of more powerful and compact neutron sources is another important area of research. This will make neutron imaging more accessible to a wider range of users. Scientists are also working to develop new detectors that are more sensitive and efficient. The development of new software and algorithms is also essential for the advancement of neutron imaging. This will allow scientists to extract more information from neutron images and to develop new applications for the technology. Neutron imaging is a powerful tool that is helping us to understand the world around us. It is being used to solve problems in a wide range of fields, from medicine to manufacturing. And as the technology continues to develop, we can expect to see even more amazing applications of neutron imaging in the years to come. Neutron imaging is a testament to the power of human curiosity and ingenuity. It is a reminder that there is still so much to learn about the universe. By continuing to explore and experiment, we can unlock new secrets and make new discoveries that will benefit all of humanity. Neutron imaging is a relatively young technology, but it has already made a significant impact on our world. And as the technology continues to develop, it has the potential to revolutionize many different fields. The future of neutron imaging is bright. With continued support for research and development, we can expect to see even more amazing applications of this technology in the years to come. Who knows what secrets of the universe neutron imaging will help us unlock in the future?
Seeing the invisible. The power of neutron imaging. Neutron imaging is a powerful tool that allows us to see inside objects without taking them apart. It relies on the unique properties of neutrons, subatomic particles that have no charge. This means they can penetrate materials that X-rays and other forms of radiation cannot. When neutrons pass through an object, they interact with the nuclei of the atoms that make up the object. This interaction can be detected and used to create an image of the object's internal structure. Neutron imaging has a wide range of applications in fields such as materials science, engineering, archaeology, and biology. It can be used to study the structure of metals, ceramics, composites, and other materials. It can also be used to inspect welds, detect defects in components, and analyze the performance of engines. In archaeology, neutron imaging can be used to examine ancient artifacts without damaging them. In biology, it can be used to study the structure of cells and tissues. Neutron imaging is a non-destructive technique. This means that it does not damage the object being studied. This is a major advantage over other imaging techniques, such as X-ray computed tomography, CT, which can damage sensitive materials. Neutron imaging is also a very sensitive technique. It can detect very small changes in the structure of an object. This makes it an ideal tool for studying the effects of stress, fatigue, and corrosion on materials. Overall, neutron imaging is a powerful and versatile tool that has a wide range of applications. It is a non-destructive and sensitive technique that can be used to study the internal structure of a variety of objects. As technology continues to advance, we can expect neutron imaging to play an even greater role in our understanding of the world around us. From film to pixels, the digital revolution in neutron imaging. Neutron imaging has been around for decades, with its roots tracing back to the 1950s. Early neutron imaging relied on photographic film to capture the images. This process was time-consuming and labor-intensive. It also limited the amount of information that could be extracted from the images. The 1990s brought about a digital revolution in neutron imaging. Digital detectors began to replace film. This allowed for faster image acquisition. It also enabled researchers to store, process, and analyze images more easily. Digital detectors also offered higher resolution and sensitivity than film. This shift to digital technology opened up new possibilities for neutron imaging. Researchers could now study dynamic processes in real time. They could also create 3D images of objects by combining multiple 2D images. This advancement led to a significant expansion of neutron imaging applications. The digital revolution in neutron imaging marked a significant turning point in the field. It paved the way for the development of more advanced techniques and applications that continue to shape the field today. A clearer view, modern neutron imaging techniques and their applications. Modern neutron imaging techniques have pushed the boundaries of what we can see inside objects. Techniques like neutron tomography, neutron diffraction, and neutron reflectometry offer unique insights into the structure and composition of materials. Neutron tomography, similar to X-ray CT, allows us to create 3D images of objects by taking multiple 2D neutron images from different angles. This technique is particularly useful for studying complex structures and identifying defects in materials. Neutron diffraction, on the other hand, helps us understand the arrangement of atoms within a material. This information is crucial for studying crystal structures, phase transitions, and magnetic properties. Neutron reflectometry allows us to study surfaces and interfaces at the nanoscale. This technique is particularly useful for understanding thin films, coatings, and biological membranes. These advanced techniques have found applications in a wide range of fields. In materials science, they are used to study the performance of advanced materials like superalloys, ceramics, and composites. In engineering, they are used to inspect welds, detect cracks in aircraft components, and analyze the performance of fuel cells. In archaeology, they are used to study ancient artifacts, revealing hidden details and providing insights into past civilizations. Modern neutron imaging techniques have become indispensable tools for research and development across various disciplines. They continue to evolve, offering ever-increasing resolution, sensitivity, and analytical capabilities. Section 4. The Chama Statue, a case study in neutron imaging. The Chama Statue, a 13th century bronze sculpture of a Buddhist deity, provides a compelling case study for the power of neutron imaging. The statue, housed in the Reitberg Museum in Zurich, Switzerland, posed a mystery to art historians. They were curious about its internal structure and any hidden details that could reveal more about its creation. Neutron imaging offered a non-destructive solution to this puzzle. Researchers used neutron tomography to create a detailed three-dimensional image of the Chama statue. The images revealed the presence of internal supports, casting flaws, and even traces of the original clay mold used to create the statue. These findings provided valuable insights into the casting techniques used by ancient artisans. The neutron imaging study of the Chama statue highlights the importance of this technique for studying cultural heritage objects. It allows researchers to peer inside these precious artifacts without causing any damage. This information can help us understand the techniques used to create these objects and preserve them for future generations. The Chama statue serves as a testament to the power of neutron imaging in unlocking the secrets hidden within cultural heritage objects, offering a glimpse into the past and informing preservation efforts. Section 5. Collaboration in crisis neutron imaging research during the COVID-19 pandemic. The COVID-19 pandemic presented unprecedented challenges to scientific research, disrupting access to facilities and hindering collaboration. However, the neutron imaging community responded with resilience and a spirit of cooperation. Researchers around the world joined forces to share resources and expertise, ensuring the continuation of vital research. During the pandemic, many neutron facilities implemented remote access protocols, allowing researchers to conduct experiments from afar. This ensured that valuable beam time was not wasted and that research could proceed despite travel restrictions. Scientists also collaborated on the development of new techniques and applications for neutron imaging, focusing on areas relevant to the pandemic, such as the study of antiviral drug delivery mechanisms and the development of new diagnostic tools. The pandemic highlighted the importance of international collaboration in scientific research. The neutron imaging community demonstrated that even in the face of global challenges, researchers can come together to find solutions and advance our understanding of the world. The COVID-19 pandemic, while disruptive, ultimately showcased the adaptability and collaborative spirit of the neutron imaging community, paving the way for new ways of working and accelerating research in critical areas. Section 6. A bright future. New opportunities in neutron imaging. Recent innovations in neutron imaging have opened up exciting new opportunities for research and development. The development of more powerful neutron sources, advanced detectors, and sophisticated data analysis techniques has pushed the boundaries of what we can see and understand. One of the most promising areas of research is the development of compact neutron sources. These smaller, more portable sources could make neutron imaging more accessible to a wider range of researchers and industries. Another exciting development is the use of artificial intelligence, AI, in neutron imaging. AI algorithms can be used to analyze large data sets, identify patterns, and automate image processing tasks. This can significantly speed up research and improve the accuracy of results. The future of neutron imaging is bright. As technology continues to advance, we can expect to see even more innovative applications of this powerful technique. From studying the behavior of materials at the atomic level to developing new medical treatments, neutron imaging is poised to play an increasingly important role in shaping our understanding of the world around us. Neutron imaging has come a long way since its inception. With ongoing advancements in technology and a collaborative spirit driving research, we can look forward to a future where neutron imaging unlocks even more secrets of the invisible, leading to breakthroughs in various fields and enriching our understanding of the universe.